Thanks so much for
yeah, you're welcome. Here, this is yours. Okay, so we're good to go?
Yeah.
Okay. So once we run density or DFT and get the ground state electronic configuration, I guess the first thing that you can do is take a look at the band structure, and in the hydroxyl case, you'll notice that the upper edge of the valence band is in the, the upper edge of the valence band is localized on the perovskite, and the lower edge of the conduction band is localized on the titanium dioxide, which is preferable for a solar cell application because that will lead to a charge transfer once the photoexcited charges relax to the frontier orbitals. In the acetate model, however, you end up with both of the band edges being localized on the titanium dioxide. And so if you do get a charge transfer, it's likely to be very short-lived, not preferable for extracting those charges because both of the photoexcited charges are likely to land in the titanium dioxide, just exciting that one species energetically. And so once we have the ground state electronic configurations, we can calculate the transition dipoles and the oscillator strengths in order to figure out the absorption spectra. And so there's a pretty negligible difference between the two of these. In the acetate model, the absorption gets shifted slightly upward generally, and the D peak kind of gets squished a little bit, and the B peak seems to get perked up a little bit, but there's no significant difference, which suggests that the perovskite is essentially responsible for all of the light absorption, for the most part, anyway. Okay, so once we have all of that ground state, the ground state observables figured out, we move on to molecular dynamics. So I heated the system to 300 degrees Kelvin over, it's on here somewhere. Yeah, over the course of 300 femtoseconds at half femtosecond time steps. And then molecular dynamics was run for a picosecond with 1 femtosecond time steps. And so from that, we can calculate the couplings between orbitals, between adjacent time steps, and use that information to calculate a Redfield tensor. And small portions near the frontier orbitals are shown here. You can see that essentially what these represent is basically transition rates, I guess, from this orbital to this orbital. So you can see that it essentially only really allows for transitions between neighboring states in both systems. I mean, there's a slim chance that you could go some other route, but that's not, I guess, the likely path that it will take. And so these plots show the actual orbital occupations as a function of time. So each slice of this represents the occupation of one orbital, where the height is the occupation of it. And then time is represented on this axis kind of going off to the right here. Yeah, I guess that kind of supports what I was just talking about with the Redfield tensors. And then we can also make these graphs down here, which I need to make the fonts a little bit bigger on, because that's impossible to read. But so I guess in these graphs, the green background color represents no change from the ground state charge distribution. The darker blue and purple color represents a positive charge localization, so that'd be a high hole density. The brighter yellow and orange represents a high electron density. So these top graphs both show the the energetic distribution of charge as a function of time. The time axis is logarithmic, by the way. And then these bottom ones represent the spatial distribution of charge in the z-axis. So these two models are shown here so that you kind of can compare, you know, where this is on the actual atomistic model. So, I mean, at the end here, you can see that you've got a high hole density localized right at this top layer of the perovskite and a high electron density on this bottom set of titanium, of the titanium dioxide. So this actually is a charge transfer state in this case, whereas in the acetate model, you kind of have a very scattered charge distribution here. You get a slight backwards charge transition from what we're looking for in this device, and then both excited charges end up on the titanium dioxide as the system relaxes. And these were both chosen to be the transitions that had the highest oscillator strength for both of these. And I guess so I looked at, you know, the top 20 oscillator strengths for each of these systems and calculated out the relaxation times for each of those. And on these figures, you can kind of see where that is by when the electron and the hole density sort of, it stops changing, I guess. You know, it ends up landing somewhere and then stays there. So at that point, it's done relaxing, so there's your relaxation time. And I don't have enough room to try to squeeze all of this stuff, so I have this over here for now. And so this is my plot of relaxation times for these systems as a function of dissipation energy. And what I mean by dissipation energy is in the case of electrons, it would be the energy difference between the photoexcited state and the LUMO. And in the case of holes, it would be the energy difference between the HOMO and the photoexcited state of the hole, I guess. The state that the electron left upon photoexcitation. So you can kind of see that, you know, there's local energy gap. It obeys the energy gap law in local segments, but it doesn't appear to obey the energy gap law globally. At least in most cases, I guess the acetate holes seem to, and the holes kind of seem to obey the energy gap law. I guess the electrons don't really. I guess I don't really know why that would be. I'm still not really totally sure.
Ask your group.
I don't know if anybody has any insight as to like
maybe
the
some
conclusion I
hints
can draw from that.
in written form or privately later.
Yeah.
It may deal with different density of states, sparse or dense, and if absolute value of density of states is different, and also how the density of states changes as we go further off from the gap. So if the gap law is designed for sparse states, but if it is denser, there are chances to jump through the neighbor, and instead of slowing down, it could be acceleration.
Like if you scroll up to your PDOS, visualize it. Like the holes have at least 2 times more density of states.
Yeah.
So that could be one reason.
Okay, yeah, I guess there's just more likely to be kind of a straight shot down as opposed to kind of having to skip over. By the way, if anybody has any suggestions on like what I should try to cut out of this middle section, including, you know, this plot down here, because I would like to try to get, you know, whatever I'm going to do for my last project onto here if possible, and then, you know, the new project over in this side. But obviously I don't quite have room for that, so something has to go. I don't know, whatever seems the least relevant, I guess, just let me know. So then for the new project, I generated a whole bunch of coupling stuff for, you know, doing the whole Redfield analysis again. Unfortunately, the trick that I did to make it work made my data useless, so I gotta redo that now. But I guess this is the atomistic model that I'm looking at manipulating with an electric field. So you have cesium lead bromide perovskite, the same as in this case, and then you have the titanium dioxide from the hydroxyl model over there. It's all the same model. The difference is that we now have a whole transport material, namely spiro-ometad. And so what we're trying to do in this case is figure out how the excitonic behavior responds to an electric field. And so...
Be careful with the word excitonic. If you're not sure, tell excited state.
Okay, yeah. Well, because I know an exciton is like...
It's a quasi-particle when
yeah.
electron and hole are bound and move together.
Yeah.
So and it is exactly the audience who will pick you on the inconsistencies.
Yeah. So I took 100 states above the HOMO, or sorry, below the HOMO and 100 states above the LUMO, and integrated out 2 dimensions so that only, you know, this dimension is left, and plotted their densities in here. So each of these slices represents an orbital, and the this axis here represents, you know, distance in that model in angstroms. And so you can kind of see where each band is localized as far as what species is on here. Yeah, just a nice visualization, I guess. I don't know if I should really say too much about that or not. And so in the ground state, what we're doing is approximating, well, I guess maybe it's better to say we're calculating how the ground state we're figuring out how the energetic distribution of the ground state orbitals responds to the electric field. And the way that we are calculating that is by using a first order dipole approximation.
Which you may navigate us right now.
What's that?
Show which equation illustrates your words in the figure.
Oh, maybe that's right across. That would be these equations here. So this one in particular is what we're really looking at. And so the nuclei represent the positive end of the dipole, and since that's constant for every orbital, that never changes, you can essentially just remove that from the equation and you still get the same relative structure that you would have otherwise. So we use this equation with the only real difference being this vector is just replaced with a scalar since it's pointing, you know, straight up or straight down, and this r vector is replaced with the z position.
We keep scalar product, but we intentionally orient electric field along the z-axis so that vector consists on z projection.
Yeah. So you just end up with the magnitude of this times your z position of your orbital.
So z projection of field times z projection of diagonal.
Yes.
How this equation corresponds to the previous one? Is it the order correction or it is lowest order in perturbation theory?
It is the lowest order perturbation theory.
Why wave function is not changed? Why you assume that wave function is not changed by this perturbation?
Because that would make calculations much more difficult, I guess.
No.
I don't know.
Ask Aaron. He was getting credit in the advanced PChem on the subject, and he may give you the answer if you organize to him.
I had no scalar correction?
In the first order perturbation theory, wave function didn't get any change. It's only energy that is being corrected to the first power of the interaction matrix element.
Right.
And if, in order to get corrections to both energy and wave function, one needs to move to the second order correction, which is like negligible compared to first order if the interaction is small. So it is not free rules decision because it is easier.
Okay.
It is literally dictated by rigorous perturbation theory that if you are in the first order, there is no change to wave functions.
Mm-hmm. Okay. Should I change the wording here then, do you think? Because I mean, I guess that would technically still be kind of accurate. I mean,
You can just remove eigenenergies of Kohn-Sham Hamiltonian
oh, okay. Yeah.
or energies of orbitals. You will hear some suggestions from audience. Yeah, not quite correct.
Okay.
First
So.
order, oh, sorry, that's not. So first order corrections don't mix states?
Correct.
Yes.
I guess I'll just have to look at that quickly. Because I remember there was one where it was.
There is time independent perturbation theory. First order is really easy.
Yeah.
It's just one matrix element of interaction Hamiltonian gives correction to the energies. That's it.
Oh yeah, I guess. Now let me make this hard.
Okay. So, by using that approximation from first order perturbation theory, we can calculate out, the energetic redistribution of the ground state orbitals. And that looks like this. And so what we did is we calculated out the what magnitude of electric field you would need in order to make the HOMO actually meet the LUMO in energy. So that's what you can see here with this horizontal line. And so as a first order approximation, what I'm trying to do right now for molecular dynamics is I'm taking the molecular dynamics trajectory without an electric field, and then I'm computing the couplings between adjacent time steps without an electric field, and then with these two values of an electric field, because I guess the electric field is not likely to have a drastic impact on the actual trajectory itself. I mean, it shouldn't change anything in significant enough of a way, I guess, to alter how strongly the electronic states are coupled, because you still just kind of have nuclei moving around, I guess. I don't know. And so once I get that data, then
London?
Yeah.
I've missed the pen, so I will not write, but you verbalize it. The model has both positive nuclei and negative electrons.
Yes.
Which but net total charge of a model is 0.
Mm-hmm.
So the center of mass of a model will not move
Okay.
due to electric field. Therefore, you can approximate that you can neglect influence of electric field on the trajectories.
Okay.
But if for a larger value of electric field, of course, there will be some change in trajectories.
Mhm. I guess I don't know how large this electric field actually is. I can't really visualize EVs per angstrom.
What
That's
you
just
have
giving me
is
warnings.
already is already strong enough.
Yeah.
There is no guarantee that you are in the small field regime. You may add notations or like arrows telling where is the valence and conduction band on this diagram, just to help reader. Okay.
Yeah. Yeah. So the best way to do that would be off the top of my head. Yeah, so I guess I'm going to, I thought you sent me a script that like rewrites the energy pop file. I don't know, I couldn't find it earlier today. I was
I
looking for it.
can resend it.
Okay, yeah, because I was just going to write up a new one here. Like, I rewrote the script that did this. There was like a very small logical error in it. So, I don't know. But yeah, it shouldn't be too bad. I don't know, whatever. So yeah, I'm going to calculate the new density of states in the new absorption spectra, you know, assuming these orbital energies. And so I'll have, I guess, you know, like 3 of those to kind of compare with each other. And so if anybody has any suggestions on how best to try to use this space to do that, I'm all ears. Because if I expand this out, then this is going to take up the whole freaking column. But I don't know what I would be able to kind of sneak in along the side of here, if anything. Yeah, I don't know. So I'm also going to have this sort of stuff that I'm probably going to try to, you know, put up next to each other.
It would be great if you take probably all the space.
Yeah.
And if it is too late and you do not have time for any changes, and you are not comfortable with white space, mark white rectangle and write comments and emails if you need preprint of this work.
Yeah. That's my poster.
Okay, let's thank London. Any questions or suggestions? If no, please collect written feedback, if any. And we need to go across 3 posters at least in the remaining hour. And now, for sure. No.
I just closed mine out.
You put the one by Fatima, and let's put the one by.
I guess for time, I'll just skip past most of the introduction stuff that we normally do, but I guess I'll say basically that we're looking for polaron formation and white halide perovskites, which have been known to, or it seems like an intrinsic feature of these materials in the excited state that they form polarons for both positive and negative charges. And for my title, I try to make a play on words. When life gives you lemon, make lemonade. So usually people avoid polaron formation because it's not good for photovoltaics or charge migration, but if life gives you localized charge carriers, try to make light. I don't know if people get that at first, but yeah, so we're going to try to take these polarons and make them emissive in the IR region, because some experiments have shown that polaron absorption happens in the IR region where people would be interested in getting an efficient IR emission. And just to illustrate polaron formation in these materials, so this is a 2D projection of our perovskite cluster, our nanoparticle, surrounded by passivation ligands. And this black line represents an isosurface of adding an additional electron or negative charge into our cluster, and then these arrows represent the migration of cesium atoms inside the perovskite structure, because they have positive charges and they're going to reorient around due to the negative charge that's introduced. And that's what happens in space. And then for the polaron formation, polarons have bound states. And in the spirit of Walter Cohn, you can approximate those bound states as like averaged of the electron interacting with the average ionic charge that's moved around it. So it's kind of like the Coulomb interaction. You kind of see the energy spacings will ideally follow the same type of trend. We have our electron at the lowest bound state, and then the bound states take on hydrogenic wave character. And So we have our model, we have an idea of how polaron formation forms, and what we try to do is we try to calculate photoluminescence quantum yield. So we calculate radiative recombination rates using Einstein coefficients from our spinor cone-sham orbitals, and we use red field theory to determine non-radiative relaxation in these materials. And so the methods. So traditionally, when people were first working on these problems, there's a man named Froelich who attempted to try to solve this problem. So, and the Hamiltonian he came up with was kind of the standard Hamiltonian. So you have the electron degrees of freedom, your independent phonon degrees of freedom, and then polaron formation is the coupling between electrons and phonons. So you have a cross term in there, and then these is just the convenient second quantization ways to represent these. So you have your electronic energies, your phonon energies from your creation and annihilation operators, and then you have the off-diagonal elements which couple electronic and nuclear degrees of freedom. And they have a bunch of, I guess I'm just gonna have to work on describing the couplings and then the parameters in them a little bit better, but we don't have to go too in depth to them because we're going to approximate them using cone-sham DFT. So we assume that our electronic and nuclear energies, we can just use the adiabatic states for the ground state, or for our ground state method, and then to approximate the polaron formation, we add an additional charge and let the model optimize around that charge. And that's represented by this plus delta R. So a little bit of nuclear change around it. And then the rest for their theory that I'll get into right now is how we calculate our excited state dynamics. So we calculate non-adiabatic couplings on the fly. Using spinor cone-sham orbitals. So these spinors are made up of two components, spin alpha and beta. So that's why we have two components here, And we compute those, and then we process those, which I'll describe later, to fit into our Louisville von Neumann equation. And then essentially it gets lumped into the dissipative part of our equation. So it describes dissipative transitions during a molecular trajectory. And so from here, I'll just describe some of the models or some of the calculations that we did and how we visualize, or how I'm going to attempt. I'm going to attempt to explain them using these visuals. And so to calculate binding energies, we need a reference energy to our polaron formation energy. So to do that, we use a Frank-Condon approximation, which essentially is you either put in either just a single electron or introduce a single hole or both into the model, and then just do a single point calculation. So you don't let the ions move or optimize around the new charge. So that's kind of the definition of a Frank-Condon transition. And so we calculate those, and then we are looking at various different models, or different polaron formations first. So what we attempt to do is look at either a positive polaron or a negative polaron, or injecting just one charge into each of them. So here's a negative polaron, so we just put in an additional electron, and then let it optimize to form the polaron bound states here. For the negative polaron, the same deal with the polaron, we remove a charge or add in an additional positive charge, and then let the system optimize. And then eventually we want to get to the point where we feel confident about these results and then model a photo-induced polaron. So you have positive and negative. So you photo-excite, and then eventually they dissipate to the band edges and then form a polaron. And then from there we'd be able to get optical transitions in the polaron regime, and then also transitions across the gap for the polons. So model both of those at the same time. And then another model that we will eventually try to get to, which I've been playing with, is looking at how nuclear reorganization affects the efficiency of IR emission for the polaron. So since the energy spacings are so small that small reorganization energies might actually have a big influence over the how well they emit, because from market theory, there's an inverted region for how efficient your emission can be. So there's like an optimal point where you want your reorganization to be. If you're away from that, your emission's not going to be very good. So we're trying to incorporate that into our models as well, because the Redfield theory typically doesn't account for reorganization energy. And so this is the band picture, and this is what would be like the traditional market picture. So this black line is our ground polar-on state. And then this parabola is the excited polar-on state. And this image is actually wrong. This state should be over here quite a bit. I have to play with the code to get the potential energies to line up well, but I'll have to do that. And then this line just represents the wave packets initialized on the excited state. And
Did you zoom in on that? It's not really clear on like the printed versions I hear.
on this one?
Yeah. So it looks like there's a little bit more going on than like what I can see on
There's not. Oh, you probably don't see the gray line very well. So there should only be 3. I won't let me zoom in anymore. But there's 2 parabolas, and then here it's just a Gaussian centered at the middle, and then I just zoomed in so you can't see the top of it.
Okay.
So it's just a cutoff Gaussian. And then these are the typical Marcus-Rate equations, where for our couplings we have non-adiabatic couplings, which we calculate, and then we can also for non-radiative transitions. And we also compute the reorganization energies, and we play with temperature as a parameter to see how the rates are.
What is the rate of lambda divided by delta G? Which one is bigger? For the figure that you are showing.
It's a good question off the top of my head. So delta G.
You can see it from the figure, if the figure corresponds to a realistic situation.
Well, this one, delta G, is much bigger than the reorganization.
Or smaller. So what's the definition? What delta G is much bigger than reorganization energy. Yes. Yes. Negligible reorganization. Yes.
Right, for this picture. But this one should be shifted off a little bit more.
Yeah.
So in reality, so the picture is a little misleading.
Okay.
But yeah, I'll make sure to.
Because if they're really one under each other, then it is really all our approximations are really great.
Right.
To neglect any reorganization.
Mm-hmm. And so, like I said, these 2 last models are things we want to do in the futures. We don't have enough data to fully present on them yet. So for the rest of this talk, we'll be focusing on the negative and the positive polarons. And so the first set of results is focusing on just the ground polaron bound state. And so for both of them, I can show density of states for the valence band, because that's where the positive polaron is going to be. And black line represents the neutral or non-polaron model, just the regular ground state model. And you can see for all of the polaron models, and I guess I didn't mention that we look at different multiplicities, or like spin states, so singlet, doublet, and triplet for all the polaron models. And that's what the colored lines represent. And the density states are basically all the same for the polaron models. And then they show a slight shift, or like the band gap across the gap widens a little bit for all the models. And so that's density states. And then using the Frank-Condon transitions, we calculated binding energies for all the polaron models, and they range in like the 100 millieV range. One of them's a little lower than expected, but the doublet and the triplet both show values that have been comparable to other results in the literature for whole polarons. So those seem pretty successful. And then we also compute IR spectra for the positive polaron.
Is it absorption or emission?
This is absorption. So ground state or polaron absorption. So IR spectra, so the units are in wave numbers, and the issue I had last time was I didn't change which column I was plotting. So this one should be right. So this would be the lowest energy transition.
Okay, so it will be like
It's like
0.05
Mm-hmm. Yep. For the singlet and the triplet anyway, they have about the same absorption onset peak.
And those are only electronic transitions, because in the real experiment they can be intermixed with
Surface vibration.
yeah, just vibrational transitions, which are also in this, especially
Yeah, like this, like
1500. Yes, yes.
Yeah.
For any organic, it will be
Mhm.
strong peak.
Yep, so these are just electronic state to state transitions in the potential well.
Okay. How would you justify that you are not showing vibrational contributions into the absorption spectrum?
I guess we don't have any. I guess I'd say you don't have
I
any.
have a cheesy argument, which I'm not sure. Please correct me. It's just if we will asymptotically lower the temperature to absolute zero, the relative proportions of electronic contributions to infrared range and vibrational contributions will change ratio.
Mhm.
The vibrational contributions will never get to zero, but since they differently react to change of the temperature, we will be able to extract all the electronic transitions.
Mm-hmm. I guess an experiment, it's time resolved.
Uh-huh.
So you have like the ground state reference that has all the absorption. If you assume the excited state, there's not many additional vibrational peaks.
Great. It's another idea. If it is femtosecond experiment, which is quicker than any period than any nuclear vibrations, then there will be no chance for quantized nuclear degrees of freedom to appear there.
Mm-hmm.
If it's like 10 femtoseconds or 50 femtoseconds, it will be all the electronic transitions.
I think the Aspire paper was on, I think it was on like 10 picoseconds, because it takes at least a picosecond for the polaron to form.
Just keep thinking on background, you may get this question.
Mm-hmm. Would that be along the lines of whether, like, they're actually measuring polaron absorption?
Mm-hmm.
Okay. And I'll just mention the oscillator strength, so the color codes here correspond to the arrows in the spectra figures, and they have, I guess the numbers don't mean much, but they're moderate compared to the negative polaron for the other model that we have.
And there is no reason to compare to neutral reference state, because it doesn't absorb in this range. If you have no polar intrinsic system, that it will start absorbing like at 15,000 inverse centimeters.
And then same deal with the negative polaron, so calculate conduction band density states. You compare between the neutral ground state model and the polaron model, and we see another consistent shift which widens the band gap of all the states. And then there's not much difference between all the multiplicities for the states. And the binding energies for these did not come out as nicely as the whole model. There's a wide variance between them. So the singlet shows about 200 binding energy, so it's in the well. The doublet basically showed no binding energy, and the triplet had an unbinding, or it showed negative binding, which means that the Condon transition had a lower energy than the.
So it was what Ben Jeffrey was showing, something like transitions with negative frequency.
Mm-hmm. Yeah, and comparing that to other results in the literature, they found for, I guess, a similar model for computation. Their binding energies were on like electron volts consistently for their models, so like 1 eV. But the main difference they had, it was like an actual cluster. They didn't have ligands, so you could possibly argue that ligands suppress some of the nuclear reorganization at the surface, but there's probably a little bit more at play. There's probably a miscalculation somewhere too, so I just have to go back and double check those. Yeah, so then moving on to the IR spectra, and so for this model compared to the positive polaron, its onset is at a higher energy, so about 1,000 wave numbers, which is like 0.2 eV. And all the multiplicities have it in about the same area at about 1,500 eV. And they all have, well, I guess they all have higher oscillator strengths than the positive polaron models for the lowest energy transition. So that would kind of indicate that if there was polaron emission or absorption of the negative polaron would be a more likely candidate, possibly, than the positive polaron. And so that's density of states and spectra for the model. And then now we'll move on to excited state dynamics. I just want to rotate my figure. Okay, let's do. So for right now, we only have results for the positive polaron excited state dynamics. I know I have some calculations going for the negative polaron, and there's, well, hopefully the collaborator has some calculations going as well too, so that we can have some results for the negative polaron within the next couple of months. So we start by showing, or to, I guess to do our dynamics, we actually have to couple electronic and nuclear degrees of freedom. So we do that using adiabatic molecular dynamics. And these figures show the energy fluctuations of the cone-sham orbitals along the trajectory. So these fluctuations correspond to coupling to phonon modes along the trajectory. And if you've taken enough statistical mechanics, you probably have it burned into your mind that fluctuations lead to dissipation. So that's why we start with showing energy fluctuations of our models. And
sounds impressive.
I'd assume people at this conference would. So they'd probably be tortured with it enough, so they probably remember it. So you have fluctuations, and so to extract those fluctuations, or to extract the nuclear degrees of freedom that couple to electron degrees of freedom, we do some post-processing. So we do correlation functions, or autocorrelations of our non-adiabatic couplings, which is shown in the methods, along the trajectory. And if you take the Fourier transform of those couplings, you extract out the phonon modes that couple to those degrees of freedom. So you essentially get your spectral density, and using those rate equations, we can parameterize the Redfield equations, which describe dissipative transitions. So the plus or minus describe upward or downward transitions, and the indices correspond to 4 orbital components. But at the end of the day, pretty much all we're left with is those go away. And then the positives, they have they obey a Boltzmann distribution. So upward transitions are weighted by a factor of EKT. So they're pretty much negligible. So we're basically just looking at these two terms And those are visualized as our Redfield tensors at the bottom here, which represents state-to-state transitions between orbitals. So our X and Y axis are orbitals, and then the Z components describe rates of transitions between the orbitals. And then I guess what I have to do next, I did some playing around, so basically just condense this, widen this out, move this up, and then put our green figures, our dynamic figures here to show. I guess I have to think about it because I guess we could show like a green figure from, or no, since I'm doing positive, I can just show the whole relaxation. And then at the end of the dynamics, just put a bound state showing.
For Polaroid green figures, one may want to focus on much narrower range of energies.
Right.
If it is negative Polaroid, then just plus minus half eV or less in the vicinity of conduction band H. If it is positive, then about 0.5 eV in the vicinity of valence band H.
I guess. Is there a marker here?
On the table.
I don't know what I kind of visualized doing was. Like if that's our whole.
Yes.
And then at the end of that, putting. Showing that after it cools. It forms the polaron. And then we calculate those transitions for our PL quantum field.
Yes.
Or to try to relate
But if
the figure to the table.
If you compute rates for geometry that is already being optimized for the positive polaron, when you go from like, okay, we'll talk in person. It's many things.
Yeah. Basically, just one more figure to put here. And
Yes,
then
yes, please.
move
And,
stuff up.
and you can put green figures of standard dynamics. Would be cool, even if they're done.
So the main takeaway, or at the end of the day, we calculate radiative rates using Einstein coefficients, non-radiative rates from Redfield tensor, and what we find is that the radiative rates are on the scale of, or no, other way around. So non-radiative is on the scale of inverse femtoseconds, and radiative is on the scale of inverse microseconds. So there's 6 orders, different magnitude. So basically the yield is 0.
Can you
these
put,
models.
instead of 0, put like 10 to the minus 6?
Yeah, I can do that.
Because 0 is suspicious. And how would the non-radiative rates change if you drop the temperature to liquid nitrogen? Can you do it without, of course, when ideally one would rerun all couplings at lower temperature, but can you just scale it down and tell that it will be like linear or according some other function like Bose-Einstein distribution will be smaller rate, and then the quantum yield will change and will become slightly bigger. If it is already 10 to the minus 6, it will never flash like crazy, but it will be a little more efficient at lower temperatures.
Well, they don't know anything about perovskites anyway.
Huh?
If they don't know anything about perovskites, because I guess the counterexample that would be if you lower the temperature.
There will be phase transformations. There will be many things.
Yeah, I can try and put something for that argument.
Did you ever think about transient absorption? If this model doesn't emit efficiently, but when it is already excited and system experiences population jumps from state to state, then there will be additional transitions available for absorption, so time-dependent absorption. And it is one of the available spectroscopic probes that could be already reported in experiment or will be reported soon because it is an inexpensive experiment.
I know it's on whenever we get oscillator strings. Or I guess I could just use the ground state oscillator strings. I don't have.
You use ground oscillator strings for polarics.
Right, and just do that for the dynamics.
Probably no time for the contrast next time. Let's thank Aaron. Any questions? If no, there is a hope, at least Aaron has hope that there are some written comments for him. And in the remaining half an hour, we plan to complete two. So, Felipe, would you like to guide through your poster? So, Daniel, probably you present on Friday.
Okay.
You see it's not very practical to squeeze.
I can present Friday.
Yeah, thank you. Yeah, Daniel, just a second. Daniel wants, or at least he doesn't object to present material based on higher level calculations that we all may practice in years to go.
Yeah. So we are interested to silicon nanowires because they have some optoelectronic properties such as band gap, radiative, non-radiative transition. And all of them are dependent on moment of dispersion along the growth direction. Here we calculated non-radiative lifetimes of electrons and holes for two silicon nanowires grown in 001 and 111 directions. With momentum conservation and without momentum conservation. And we tried to calculate photoluminescence, that is, for photoluminescence, momentum is conserved. As you can see here, the band structure of these two silicon nanowires. So if light pulse is applied to the silicon nanowire model, electron can travel from valence band to conduction band. And on the right panel, we can see how photoexcited electrons come back to the valences. So there are two pathways. For one pathway, electron can come back to the band edge through same K point, and electrons can come back to the different K points. So if electron comes back to through same K point, we call momentum restricted. If electron travels through different K point, we call it momentum unrestricted. There are many pathways here. I just showed a couple of them. Now the methodology. So we used for calculating electron lattice coupling, we used one electron quantum equation, and the solution of this equation is this one. One electron quantum wave function. As we know, upon photoexcitation, electron travels from valence band to conduction band, and they come back to the band edge. When they are coming back, they can couple with the nuclear. nuclear motion. So, and using this equation, we can calculate the electron, the coupling between electron and nuclear. That is called non-adiabatic couplings. Once we have this non-adiabatic coupling, we can derive autocorrelation function here, and using this autocorrelation function, our rate of transitions can be calculated.
So for autocorrelation function, how many indices are available for coupling? Coupling V, each the coupling comes 2 times, right?
Mm-hmm.
V ij k prime, and then V kl k prime.
Mm-hmm.
Why? And neither one of these 4 indices should coincide generally.
So here this is time at time t, and this is t plus
Yes.
for
For
2
our
time steps.
for practical calculations, we often make some indices coincide because we are looking on the segment of red field. But if we write down general equation, it should be different indices. Like here, band indices are different. Ij, right?
Oh, okay. So
And
I
here you
need
have
to write
KL.
m or something.
No, IJKL is okay. M is better just so that it doesn't interfere with letter K, but for band indices are okay. But then for momenta, it's like KK prime, and here should be like double prime and triple prime. And here two indices more, so like 8 indices. It doesn't change things for practical calculations, but in the environment where we will come, some may object.
Okay, so all of them should be different K points.
Yes.
Okay.
Yes.
4 K points total.
Yes. Yes.
Okay. And one can derive rate field tensors from the rate of transitions. Here is the time evolution of density matrix, which uses energy dissipation. And the last term is electron energy dissipation term.
See, here you have for
4,
red field
yeah.
tensor, it's right amount.
Okay, and then we can calculate the non-equilibrium charge distribution, which is a function of energy in time. Here, this term is the equilibrium charge distribution. And at low temperature, this term is if index I is less than or equal or more than 1. This is the direct delta function. And this is also summation of all states.
For your low equilibrium, it has all the indices for bands, but doesn't have indices for K. Should it be also?
This is charge distribution.
So it's already you perform summation over K. Just let's discuss or think about if additional indices are needed.
And this is the expectation value of charge carrier. We assume a single exponential function to fit this energy dissipation to get the rate of relaxation of charge carrier. And this is a equation for calculating relaxation rates of charge carriers. Using this equation, we can calculate the photoluminescence, but there is one term missing here. There is oscillator strength. Need to fix it.
Exciton, put maybe excited state dynamics. before this equation for photoluminescence, put excited state. Because in the approach that we practice, there are no accidents.
Oh,
really.
accident.
Our electrons and holes do not
Okay.
interact.
And here, probably I need to change this name also. So as we know that there are 4 K points here, and for each K point there are 80 orbitals. And in order to calculate further electron dynamics and relaxation rates, we need to combine all of these orbitals in a single file. This table shows how those bands are arranged in that single file, which consists all orbitals for all 4 K points. For here we can see 2 indices. I is for HOMO and J is for LUMO. We consider this is the energy of that particular band. This is momentum variable. I mean which band it is and at which K point it indicates this column. And these are the initial state. These states, this number we consider when we calculate this electron dynamics, relaxation rates. So, in order to calculate electron dynamics and relaxation rates, we consider this initial band number. So, HOMO we consider 1 and LUMO we consider 1 for. HOMO we consider 1 for hole and LUMO we consider 1 for electron. And these are the numbers. So in that single file, which consists 320 orbitals, 160 is the HOMO. Since we consider 40 states above LUMO and 40 states below HOMO, so we consider from 81 to 120 and 90. 120 is the HOMO. So 40 times 4, 160. That's the HOMO for that resulting file, which consists all of the orbitals for further calculation. And 161 is LUMO. Then continues here. So if we consider calculation of photoluminescence, these 2 states should be same. We can see for this column for silicon 100 and this column for silicon 111. Here we can see these initial states, I would say. They are same. Like, it is 65 in that single file, what I described before. So since there is 65, so that's LUMO plus 17 and it is at gamma point, and HOMO minus 17, that is also at gamma point. These are the absorption spectra here. Here I consider different states. It's not the same states. Same initial states for the electron and hole. This is not completely photoluminescence, it's dynamics of exciton, so we focus on dynamics of photoexcitation starts at I think 4.6 or something. And this is time integrated emission spectra, but time resolved emission spectra is missing here. So this calculation is not completed. Something needs to be fixed here. This is electron relaxation rates for electrons. These graphs for relaxation rates of holes. there is a difference between these two graphs. Here we considered only 10 states are above HOMO, below HOMO, and 10 states above HOMO. But here we consider 10 states based on the highest oscillator strengths. The same thing happens here. This is for 10 states below HOMO and 10 states are above. 10 states below HOMO and 10 states above LOMO. And this is 10 states for highest oscillator strengths. These, and we can see here for a couple of initial excitation, these initial transitions, they follow gap law, and after that they follow inverse gap law here as well. But for them, for holes, we can see they follow the gap law for most of the gap arcs. And this figure is supposed to go here. So these figures just show how electron and hole travel from excited state to the band edge. So this is initial. These are actually snapshots from video clip. So this one is initial step, and this is final. And this is for initial.
Can I interrupt?
Sure.
So, if possible, I know that time is up, and it could be not enough time, but the energy. So this function has two components. Y is energy, and x is momentum. For energy as function of time, you show the equation, and you can even make an arrow. But one may want to add another equation for momentum as function of time. It will be like very similar to this one, like this delta n, and instead of energy, put here just momentum. Yeah. Sorry for interrupting. Please continue.
Yeah, I understand. So here is the conclusion. Conclusion is we considered momentum restricted transition and all transitions which include momentum restricted and unrestricted. So in case of all transitions, relaxation is quicker compared to momentum restricted transitions, because there are additional channels to relax to the band edge for charge carrier. That's all.
Okay, thanks, ma'am.
I'm sorry, could you explain your energy versus momentum graph? Which is the hole, which is the electron,
Here?
and what are those little squiggly lines, the red and the blue, trying to indicate?
So,
I'm sorry, I'm going to ask too many questions. Which one is your hole and which one is your electron?
oh yeah, this is the valence band, this is conduction band, and these are the bands.
Okay, what is the red line and what is the blue line
It's
represent?
the trajectory of electron. So
So
electron
should-
travels this way to band edge, and hole travels this way.
Can I make a suggestion?
Sure.
Maybe draw an arrow tip on the show that movement is going this way, and then maybe an arrow tip at the red, just for presentation purposes, because I didn't quite know. I mean, I figured it was a path. I didn't really know it was a trajectory. So, but I mean, I guess it's more or less the same thing. It's a path it's taking. So, just a suggestion. I wasn't quite sure.
Okay. Thanks. Any other question?
There will be people who will look only at this figure. It's because it summarizes all your work, and it will be discussed about with great excitement. More questions? I have one quick one. So, do not erase anything, even if you find errors. Right now it's too late. But just think and try to analyze. Here, the energy as function of momentum has maximum, right, in the middle of the band. So it is 1, 1, 1,
Mhm.
right? And here, when you introduce the top of the valence band, it is at gamma point. Like, why the band structures happen to be different in these figures?
Yeah, so this is the problem with silicon 111. For calculating this, all of them, if I consider homo minus minimum state plus 1, that it doesn't work.
It could be some very easy to fix technical detail related to your table. Maybe making some tricks of swapping order of the elements in this table, how to go from number of band at k point to overall index will fix it. I don't know right now. It's hopefully it's easy to fix. If there are no more questions.
I have one last question.
And we have one more talk before the class.
Okay, the one lighter blue, does that mean anything, or is it just an artifact of the graph?
This?
No. On your far right graph, there's a lighter blue on top of your bottom. I didn't know if that meant anything.
Perfect question.
Here?
It's hard to
Sorry.
see. There's like some right.
I believe the electron density.
Yep.
Density,
Yes.
since I am considering these k points.
You said it was electron density?
Whole density, right?
Oh, whole density.
Okay.
Those are
Okay,
electron density.
cool. Forget it.
Charge density.
Charge
density.
For making it maybe more easy to understand for those who come for like half a minute, one can add color bar at a side. And when you do in MATLAB, there is a button to click it and you can get it. Okay, let's thank Fatima once again. So hopefully there are some written feedback.
Okay, so in this study, we want to figure out the gravity of the diazonium source on silicon surface. So typically, silicon surface is passivated by hydrogen, and the silicon hydrogen bond is not stable. So at elevated temperature, it can decompose. So to avoid this, we need to replace hydrogen by some ligands. For example, we can replace them by carbon rings. So because carbon silicon bond is quite stable, so at high temperature there will be no changes at all. So here is my I guess I have two goals for this project. So the first goal is to figure out how this kind of gravity reaction happen. The second goal is to find out what kind of effect will this functionalization introduce into the silicon surface system. So here is my model. This is the silicon 111 surface, and this is the diazonium molecule. So first I do ab initio molecular dynamics at high temperature at 2000 Kelvin. So this is a graph. This is interatomic distances along the trajectory. So the blue is the carbon nitrogen bond, and the red is the bromine hydrogen bond, and the green is the carbon silicon bond. So basically, initially the carbon nitrogen bond it's like 1.5 angstrom, but as time goes by, we can see the breaking of a carbon nitrogen bond. So for example, at 300 it's like 6 angstrom, That means the nitrogen is away from the carbon ring. Next, we see the formation of hydrogen bromine. This is the hydrogen bromine molecule. And finally, we see the attachment of silicon ring to the attachment of the carbon ring to the silicon surface. Because we are running ab initio molecular dynamics at high temperature, so we see the some reconstruction at the surface. So in the next part, I show the basic electronic structure of different system. So here, for this system, the surface is specified by hydrogen, and here we replace one hydrogen by the phenyl ring, and here is half the surface is replaced by the phenyl ring. Or here, all surface are replaced. So this is the density of states, and this is the absorption spectrum. So basically, we find the top three are very similar, which means the functionalization have minimum effect. But for the final figure, we can clearly see the decrease of the band gap. This is because for the HOMO, the carbon ring introduced a new state. So because the phenyl ring is kind of large, it's kind of bulky, so there is some hyperstacking or some reconstruction of the surface. And here I show the charge carrier dynamics for this system. So for example, this is the charge carrier relaxation as a function of time and energy. This is from HOMO -30 to HOMO +18. So, and this is grease for the relaxation. And this figure shows the kind of the exciter. So basically, what we did is at each time step, we calculate the energy difference between this state and this state. So we kind of follow the evolution of excitation energy. And here I show the time resolved emission. This is the time integrated emission. So I guess the most significant peak is for the intraband transition. Yeah, that's it.
Okay, but thank you. Questions?
So your dynamics was for which model? The one model here?
For this one.
Sorry, you said you didn't see much change in the density of states before or after the addition of those ligands, or those groups?
Up to this point. Wait.
Up until this point.
Yeah,
What is
until
a half ml?
Monolayer.
Monolayer, okay. So why did you not see a difference up until that point? Did you think hypothesize what it looked like?
If you see the p dots, we can see the carbon orbital is like very deep.
It's deep inside,
Yeah.
so it's so like more. You have to have more crowding on the surface to have kind of okay.
Yeah.
What will be the density of states and absorption if one removes any ligands, including hydrogens? Is it possible to say that the gap will be closed completely and it will have like much smaller absorption?
Not necessarily, because for amorphous silicon,
Amorphous silicon with or without hydrogen?
without hydrogen, we also see some band gap, right?
But it is like very small.
Right. But here it's like 0.7 electron.
And there it will be like 0.2. So what on your opinion, what is most important achievement of this work? The reaction dynamics or optoelectronic properties?
I guess just reaction dynamics.
Okay, so reaction dynamics is more important. Is there any way to quantify this reaction dynamics other than show interatomic distances? Is there a critical temperature, like if we cool it down to liquid nitrogen, would it stop the reaction? Or if it is a spontaneous reaction, would it go at 0 Kelvin without any heat? If one just places the molecule of the diazonium salt close to the surface and let it optimize, would it do the same reaction?
I'm not sure about that, but experimentally this kind of molecule is very reactive. So I know just a little bit of sonication will induce a reaction. So I guess maybe at the temperature, if we run definition like dynamics, we might see reaction as well.
Okay.
But for long
So very small activation energy.
Yeah.
If one repeats this at different temperatures.
Yeah.
Okay. Is it exothermic? Are there proofs, numbers telling that upon reaction total energy is small?
And you can calculate the energy difference.
Yeah, it's probably no time now, but for like if it is more important, then one may add a little numerical quantify. More questions to Yulin? Hopefully there are some comments on the write-up. Questions 1, questions 2, question 3. Let's thank once again. So please make last changes, interact with each other, interact with me if needed, and plan of submitting to printing like Wednesday night, if possible. And Thursday night is last date. Do not postpone submission to Friday. What else? We may see each other on Friday for another meeting, which will be primarily for Dr. Killing group, but David will present there something about. I'll announce his work. Multiple spawning approach for excited state dynamics. So some of us were running into this literature on this subject. Right? Okay, so meeting is done. There will be class here to continue.
So will it be in this room on Friday then? Or
No. The scheduled room is QVP 422 on the first floor.
422, at what
But-
time? What time will the meeting?
3 p.m.
Okay, because we have seminar at 3:30, so I don't think I can take Friday.
But one of the speakers fears cameras and asks if it is possible to do in a room without camera.
Oh, no.
And it is not David.
Okay.
Dave was not upset about that, though. Of course, it's the first they've heard about this.
What's that?